Here are two programs. Same task. Find whether a name is in a list. On 1,000 names, both feel instant. Nothing to see. But watch what happens as the list grows. Because one of these programs has a secret, and by the end of this video, you'll spot that secret in any code you read. 1,000,000 names. Program A answers in 1 millisecond. Program B takes 11 days. 1,000,000,000 names. Program A, still 1 millisecond. Program B, 31,000 years. Same computer, same language, same task. The difference is not engineering, it's mathematics. The two programs have different shapes. That's what Big O notation measures. Not how fast code runs today, but how its cost grows as the input grows. It's the single most useful lens in computer science, and despite the scary name, you can build a complete intuition for it in the next 15 minutes, with pictures instead of formulas. Let's meet the shapes, from tame to terrifying. First, constant time. O of 1. No matter how big the input, the cost is the same. Looking up a value by its array index. Checking if a number is even. Grabbing the first element of a list. The input can be a phone book or the entire internet. One step is one step. Second, logarithmic time. O of log n, the shape of halving. Every step cuts the remaining problem in half. The cost barely rises as the input explodes. Doubling your data adds one step. 1,000,000 items, 20 steps. 1,000,000,000, 30. 1,000,000,000,000, 40. This curve is why search engines feel instant. Third, linear. O of n. Cost grows exactly with input. Reading every element once. Summing a list. Finding the maximum. Double the data, double the time. Honest, predictable, usually fine, and often the best you can possibly do because you can't answer questions about data you haven't even looked at. You already run these shapes in daily life. Checking every parking spot row by row, linear. Splitting a restaurant bill, one division, constant. Making everyone at a party clink glasses with everyone else, quadratic, 30 guests for 135 clinks. And a chain letter demanding 2 forwards per person, exponential, which is why chain letters and pyramid schemes always, mathematically, collapse. Between linear and quadratic lives a hybrid you'll meet constantly. In log n, do a halving process, but pay a full linear pass at each level. It hugs the linear lines so closely you can barely tell them apart on a chart, just slowly drifting up. Every serious sorting algorithm lives here, and we'll see in a minute why none of them can do better. Fourth, quadratic. O of n squared, the shape of nested loops. For every element, visit every element. Compare every pair. Double the data and the cost quadruples. 10 times the data, 100 times the cost. This one hides in innocent-looking code, purring on test data, and detonates in production the day the input gets real. And finally, exponential. O of 2 to the n, the shape of doom. Each additional element doubles the total work. Not adds, doubles. 30 items, 1,000,000,000 steps. 50, a quadrillion. 300 items would need more steps than there are atoms in the universe. No hardware upgrade rescues you from this curve. This is the wall the universe itself enforces. Want to feel how absolute the hierarchy is? Play this game. I'll give you a computer 1,000 times faster. With a linear algorithm, you can now handle 1,000 times more data. Beautiful. Quadratic? Only 32 times more. Exponential? Your 1,000-fold supercomputer handles 10 more items. 10. Faster hardware cannot outrun a bad shape. It never could. Now put them on one chart, and you see the whole hierarchy. At small inputs, they huddle together. Everything is fast when n is 10. But stretch the axis, and they peel apart into different destinies. This picture is Big O. The labels aren't speeds. They're fates. 2 rules make Big O feel strange at first, and both are deliberate. Rule 1. Constants don't count. An algorithm doing 5 in steps and one doing just n are both called O of n. Sacrilege? Watch the curves. As n grows, 5n and n stay parallel, but n squared crosses both of them. And after that crossing, nothing about the 5 matters ever again. Rule 2. Only the biggest term survives. N squared plus 10 n plus 50? Just O of n squared. Because at scale, the biggest term doesn't just win. It makes everything else a rounding error. At a million items, the n squared part is a trillion. The 10n part is 1/100th of 1% of it. Big O is deliberately myopic. It only sees the horizon. One honest caveat. The same algorithm can have several personalities. Quicksort averages n log n, but feed it already sorted data with a naive pivot, and it degrades to n squared. So we speak of best case, average case, worst case. Interviews obsess over the worst. Engineers care about the average and about how likely the worst really is. Know which one you're quoting. And accidentally quadratic is a real genre of disaster. For years, GTA Online took 6 minutes to load, and players blamed the size of the game. Then one anonymous hacker profiled it. The loader was parsing a 10 megabyte list with a function that rescanned the whole string for every single token. Classic hidden n squared. His fix cut loading by 70% for a game earning $1 billion a year. This myopia is a feature, not sloppiness. Constants depend on your CPU, your language, your compiler flags. Yesterday's video showed constants changing 5-fold with one flag. The shape survives all of it. Big O is what remains true about your algorithm on every computer ever built, and every computer that ever will be. Time isn't the only thing that grows. Memory has shapes too. An algorithm that streams through data holding one running total uses constant space. One that builds a copy of its input, linear space. One that tabulates every pair, quadratic. And quadratic memory kills faster than quadratic time, because you can wait out a slow loop, but you cannot wait out a machine that's out of RAM. Now the fun part, algorithms that cheat their way down the hierarchy. Back to our two programs. Program B checked 1 billion names one by one, linear. Program A knew the list was sorted, and that changes everything. Guess the middle. Too high? The answer lives in the left half. Throw the right half away. 500 million names, gone, in one comparison. Have again. Each question kills half of what remains. That's the halving shape, logarithmic. And it's why 1 billion names need just 30 questions. You've used this your whole life. Opening a dictionary near the middle, flipping forward or back. You were running binary search before you could code. Can we cheat even harder? All the way down to constant time? Yes. The hash table, possibly the most important data structure ever invented. Feed the name through a hash function, a deterministic scrambler, and it outputs a number. Use that number as the slot where the data lives. Look up, hash again, jump straight to the slot. No searching, ever. This is why dictionaries in Python, objects in JavaScript, maps in Go feel free no matter how much you stuff into them. 1 billion entries, and a lookup is still hash, jump, done. It costs memory, and rare collisions need handling. But you're trading space for time, and in computing, that trade is almost always a steal. Hash functions themselves deserve 10 seconds of awe. A good one behaves like organized chaos. Change one letter of the input, and the output slot changes completely, yet the same input lands in the same slot, every time, forever. Deterministic randomness. The whole O of one miracle rests on how evenly that chaos spreads your keys across the slots. A bad hash piles everyone into one bucket, and your constant time quietly rots back into linear. So why ever use anything else? Because hashing scrambles order on purpose. Ask a hash table for everyone between K and M, and it just shrugs. Its whole trick was forgetting where things sort. Range queries, nearest neighbors, sorted listings. Those want trees, which keep order and answer in log n. Data structures are a menu of trade-offs, and Big O is the price column. Sorting deserves its own chapter because it hides a beautiful drama. The obvious approach is bubble sort. Sweep the list, swap neighbors that are out of order, repeat until clean. Every pair might need comparing, n squared. On 1 million items, that's 1 trillion operations. Your laptop, 20 minutes of fan noise. The smarter family, merge sort, quick sort, uses divide and conquer. Split the list in half, sort each half, Then merge two sorted halves, which is easy. Splitting gives you the log n. Merging each level costs n. Total, n log n. The same million items, 20 million operations instead of a trillion. 20 minutes becomes 20 milliseconds. A fair question. Binary search needs sorted data, but sorting costs n log n. Did we really win? Think in totals. Searching a million name list 1,000 times linearly, 1 billion steps. Sort once, 20 million steps. Then run 1,000 binary searches, 20,000 more. The expensive preparation pays for itself by the third lookup. Pre-processing is an investment, and Big O tells you the payback period. And in the real world, the winners are hybrids. Python's built-in sort, timsort, runs merge sort at scale, but switches to simple insertion sort for runs under 64 items, because at tiny n, the worse algorithms small constants win. Remember, Big O rules the horizon, constants rule the neighborhood. Great engineering respects both. And here's the drama. N log n isn't just clever, it's the law. For any sort that works by comparing items, mathematicians proved you cannot do better. Not with genius, not with quantum vibes, not ever. There are n factorial possible orderings. Each comparison can at best have that pile, and the arithmetic lands exactly on n log n. It's one of the rare places in engineering where we've hit the floor of the possible, and we know it. Which brings us to the edge of the map. Some problems have no known escape from the exponential cliff. The traveling salesman, shortest route through 50 cities? Checking all routes, more possibilities than atoms in the universe. Best known exact algorithms, still exponential. And a whole family of problems, scheduling, packing, protein folding, shares this exact fate. These hard problems share an eerie secret. They're all the same problem wearing costumes. Mathematicians prove that the core NP-complete problems translate into each other. Solve any single one efficiently, and the solution cascades to route planning, scheduling, chip layout, thousands of others, all at once. One key would open every lock. 50 years of searching, and nobody has found it. Here's the strange part. For all these problems, checking a proposed answer is easy. Hand me a route and a budget, and I verify it in linear time. Finding one is the nightmare. Whether finding is truly harder than checking is the P versus NP question. $1 million prize, unsolved for 50 years. Nearly everyone believes finding is harder. Nobody can prove it. So is the traveling salesman hopeless? Here's the twist. No. Exponential is the price of perfect answers. Drop perfection, and doors open everywhere. Greedy heuristics give decent routes instantly. Smarter approximations get within a couple % of optimal. Real logistics companies route millions of packages daily this way. Close enough, fast beats perfect, never. A very computer science kind of wisdom. And your daily life quietly depends on the answer staying no. Encryption works because factoring huge numbers seems to need exponential time, while multiplying them takes nanoseconds. If someone proved P equals NP with a practical algorithm, most cryptography would collapse overnight. Every padlock icon in your browser is a bet on a mathematical conjecture. Let's land this. Big O is the shape of growth, not the speed of code. The shapes, in order, constant, logarithmic, linear, n log n, quadratic, exponential. Constants wash out. Only the dominant term survives. Sorted data plus having buys you log n. Hash tables buy you constant. And some walls, the sorting floor, the exponential cliff, appear to be laws of nature. Here's your field guide for reading code. One loop over the data, linear. A loop inside a loop, quadratic. Check the input sizes before you panic. Having something each round, there's your logarithm. Sorting anything, n log n just entered the bill. A dictionary lookup, constant, breathe easy. Recursion that branches twice per call with no memoization, exponential, handle with gloves. From now on, you'll see code differently. A loop inside a loop will make your eyebrow twitch. The word sorted will smell like opportunity. When someone reaches for a list where a dictionary belongs, you'll feel it before you can explain it. That instinct, seeing the shape under the syntax, is what separates coders from computer scientists. Welcome to the second group. And be honest about where big O ends. It says nothing about the constants that dominate small inputs, nothing about cache behavior. Remember, the CPU video showed identical big O running 10 times apart, and nothing about your actual N profile before you optimize. Big O tells you which algorithms cannot survive growth. The profiler tells you what's actually slow today. You need both eyes open. Next time your code is slow, don't reach for a faster machine. Ask what shape you're standing on. Because a better algorithm on yesterday's laptop beats a worse one on tomorrow's supercomputer. Every single time the input is big enough. That's not an opinion. It's the math you now own. See you in the next one.